Hello, welcome back. Today I will solve LeetCode 743, Network Delay Time. We're given a network of n nodes labeled 1 to n, and we are given also the time it takes for a signal to travel from one node to another. We were also given the source node, and the question is, what's the minimum time it would take for signal to travel from the source node to all the nodes on the network? Let's take a look at one of the examples. Here we have a network of 4 nodes, and we are given the set of edges. Take this edge, for example, 211 means that this is an edge from the node 2 to the node 1, and it takes 1 unit of time for the signal to travel from node 2 to node 1. In this example, the source node is the node 2, and the minimum time for the signal to travel from node 2 to all the nodes on the network is 2. Because 2 to 1 is 1 unit, and then 2 to 3 and 3 to 4, it takes 2 units of time. That is the minimum time it would take for all the nodes to receive the signal from 2. In this example, all the edge weights are of 1 unit, so the most straightforward approach would be to use breadth first search to find the minimum time for the signal to reach all the nodes from the source node. However, the edge weights may have a different value. In this case, as long as all the edge weights are positive, we can deploy Dijkstra's algorithm. And that's what we're doing today. So let's set it up. We need several data structures. First of all, we need to build up the adjacency list for the graph. The adjacency list, the key would be the nodes, and the value will be a list of tuples comprise the node and the distance it would take from the key node to that neighbor's node. We have 3 edges in our example. For 2, it can reach 1, and it can reach 3. For both neighbor nodes, it would take 1 unit of time. For node 3, it can only go to 4, and it will also take 1 unit of time. Another data structure we will need is a mean heap. This will store a list of tuples, which comprise the node and also the distance value. The distance value here is the time it would take for a signal to travel from the source node to that node. And finally, we would have an array or a hash map where we're going to store the minimum distance from all the nodes on the graph to the source node. In this case, the source node is 2. I set the base value for all the nodes to be -1, so if the value is -1, then we have not established the minimum distance from that node to the source node. I'm going to deploy Dijkstra's algorithm to solve this problem, and here's the templates. This is derived from the templates I discussed in part 1 of this series on Dijkstra's algorithm. If you have not watched that video, and if Dijkstra's algorithm is new to you, I would strongly recommend that you pause the video and watch part 1 of this series before continue with this one. First step, we push the source node with a distance of 0 onto the heap. Source node here is 2, so 2, 0 goes onto the heap. Now we are inside the while loop. We take the first item off the top of the heap. That's 2, 0. And then we check whether 2 has been updated in the minimum distance table. It has not, so we will update 2 here as having a distance of 0. And then we're going to get all the neighbors of 2, and in this case, it will be 1 and 3. And we put these tuples onto the heap. Recall, the tuple that we're going to put onto the heap comprise of the node and also the distance from that node to the source node. Now, since 1 and 3 are directly connected to 2, the edge weight is the distance that we want to put in those tuples. So the tuples distance for both of those nodes are 1 and 1. Now we are at the top of the while loop. Again, we take the top item off the heap, and in this case, it's 1. So 1, we do an update in the minimum distance table for 1 as 1. 1 does not have any neighbor. So again, we're at the top of the while loop. We take the first item, and this is 3. For the node 3, we do an update on the minimum distance table as having a distance of 1 here. The node 3 does have a neighbor, and that is 4. We make a tuple with node 4 and put that on the heap. The distance between 3 to 4 is 1. But again, we are looking for the cumulative distance between 4 to the source node. So we add up the 1 here, and also the minimum distance from the source node to 3 is 1. So 1 plus 1 is 2. So we put the tuple 4, 2 onto the heap. Again, we are at the top of the while loop. We take the first item, and that is 4, 2. We update the minimum distance table for 4 as 2. The node 4 has no neighbors, so there's nothing to put onto the heap. Now the heap is empty, and we are done with the while loop. To establish the minimum time it will take for signal to travel from the source node to all the nodes, all we have to take is the maximum value on the minimum distance table. Now that we talk about the pseudocode, let's talk about real code. Here is the C# implementation. You can find this code in the GitHub links below, and you can convert that to any language of your choice. This is C# code, so we have a dictionary where we're going to store the adjacency list, and we have the priority queue, which is the min heap. The minimum distance table will be in the form of an integer array. Because the nodes are 1 to n, so that's why the array size is n plus 1. And we're going to set the base value for this array to be -1. So any node that has a value of -1, the minimum distance has not been set. And we set the minimum distance of 0 to be 0. 0 is never used anyway because the nodes are 1 to n. Now in this part of the code, we just build up the adjacency list. We take all the edges, which is in the form of times array, and we just add it to the adjacency list. Next, we put in the heap the source node, in which case is the k value, and then a distance of 0. And the priority will be determined by the edge weight. So this is the value that will determine the priority on the heap. Now we go through the while loop. This is very similar to what's in the pseudocode. And at the end, we check the minimum distance table. Now if the minimum value is -1, that means there is a node that cannot be reached from the source node, and in which case we will return -1. Otherwise, we just take the maximum value from the minimum distance table. That is the critical path, and that is the minimum time it will take for the signal to reach all the nodes. Now let's take a look if this works. And it looks good. Next time I will do another example using Dijkstra's algorithm. Hope to see you then.